Hello students, this is the second part of today's online instruction. This is the narrated PowerPoint. So, we are talking about the waves, different kind of waves. Now, we are talking about the electromagnetic waves. So, the electromagnetic waves are the light is a kind of electromagnetic waves. Okay, it is a transverse wave. Light is a transverse wave, as we learned before. So, light is not the only example of the electromagnetic wave. Other electromagnetic waves include the microwaves you use to heat up leftover for dinner, and the radio waves that are broadcast from radio station. An electromagnetic wave can be created by accelerating the charges. Moving charges back and forth will produce oscillating electric and magnetic field, and these travel at the speed of light. It would really be more accurate to call the speed of an electromagnetic wave rather than speed of light, okay? Because light is just one example of an electromagnetic wave. So, how we create the electromagnetic waves or creation of the electromagnetic waves? So, we have already learned how moving charge produces the magnetic field. A constant current produces a constant magnetic field, while a changing current produces a changing field. We can go the other way and use a magnetic field to produce a current as long as the magnetic field is changing. This is what induced electromagnetic force is all about. A steadily changing magnetic field can induce a constant voltage, while an oscillating magnetic field can induce oscillating voltage. So, focus on these two facts first. An oscillating electric field generates an oscillating magnetic field, and an oscillating magnetic field generates an oscillating electric field. These two key points are the understanding. These 2 points are the key to understanding electromagnetic wave. So, here the red represents the electric field, and this represents the magnetic field. So, changing the one field, creating the another field, and vice versa. So, these fields are propagating, oscillating perpendicular to each other. At the same time, the electromagnetic wave is propagating perpendicular to both magnetic and electric field. So, changing electric field makes the magnetic field and vice versa. So, if we go, just I mentioned that the speed of light, basically electromagnetic radiation, which is constant, which is 3 times 10 to the power 8 meter per second, which is universally constant. So, if we know the distance between the sun and earth, the time it takes to travel that electromagnetic radiation or light, it takes about 8 minutes to travel from sun to earth. So, you know from the wave equation, the velocity of the wave is equal to the wavelength lambda and the frequency f. So, if we look at the relation velocity is equal to the lambda times f, what does it mean? If we look at the relation between the lambda and f, lambda is wavelength, is simply the velocity of the electromagnetic radiation or velocity of the wave, you can see that, divided by the frequency. So, what does it mean? What does it mean? The frequency and the wavelength, frequency f and wavelength lambda has inverse relation. That means, if we increase the lambda, then frequency will increases, and if we increase the frequency, then lambda decreases. So, lambda increases, frequency decreases, frequency decreases, lambda increases. Okay, they have the inverse relation. So, we know in case of the electromagnetic waves, if we are talking about that, so when we know the electromagnetic waves, for example, the light waves is travel with the velocity approximately 3 times 10 to the power 8 meter per second in vacuum, but when it travels in other medium like air or liquid or solid, the speed of the light or electromagnetic radiation will decrease little bit. Okay. Now, we will come to that point, but let me discuss little bit about the electromagnetic radiation. So, earlier I said that it is better to say that speed of the electromagnetic radiation rather than the speed of the light, because we are familiar with the visible spectrum of light, visible range of light, which we call the light. But light consists of other rays like radio waves, microwaves, infrareds, ultraviolet, X-rays and gamma rays. So, all of these names are version of the electromagnetic radiation, which is called light. Okay. So, the electromagnetic spectrum is the arrangement of the electromagnetic radiation in the order of the wavelength. If we look at the order of the wavelength, what happens? Radio wave has the maximum wavelength 10 to the power 3 meter. Okay. So, frequency is 10 to the power 4 hertz. Okay. That is how, due to its high wavelength, that is how we can hear the radio sitting inside the building. We can send the signal from here to the Mercury by using the radio waves. Just we can send the signals from the radio waves because of its larger wavelength. If we look at the microwave, okay, then it decreases the wavelength. Then if we see the infrared, it has less wavelength than the microwave. Then we have the visible light, which has the wavelength 0.5 times 10 to the power minus 6 meter. So, that is the range of the electromagnetic wave we can see, which we call the light. That is not totally the light, that is only the visible range of light. Then we have the ultraviolet, then the gamma rays, and then X-rays and the gamma rays. They have the very high frequency. As I earlier mentioned that as wavelength decreases, then the wavelength when the wavelength decreases, then the frequency increases. Frequency increases means the energy increases. Okay. So, we can say that visible light is only the small portion of the spectrum. So, now you can deal with this problem. So, which of the following travels the slowest? Which one? Radio waves, visible light, X-rays, infrared light, they all travel at the same speed. You can pause my narrated PowerPoint and you can think. So, which is the correct answer? Okay, here you go. E is the correct answer. Why? They all travel at the speed of same speed, because radio waves, visible light, X-rays and infrared light, they are the electromagnetic waves, and electromagnetic radiations travel in the vacuum in the same speed. Okay, 3 times 10 to the power 8 meter per second. So, E is the correct answer. So, speed of light appears to be reduced when it travels through the a material, as I already mentioned that. So, depending on that, how fast the light travels in the medium, we have the index of refraction, okay, which is called N, which is the refractive index, which is equal to the speed of light in vacuum, which we call the C. C is simply the 3 times 10 to the power 8 meter per second, and speed of light in the material V. Okay. So, which we call the refractive index. So, how we can define the refractive index? It is the indication, the refractive index is the indication how fast the light can travel in a medium with respect to vacuum, okay, which is universal constant, right. So, this is the refractive index. So, let us talk this table, typical indices of refraction. You have the different material through which light can travel with certain velocity, that determines its index of refraction. So, in vacuum, the index of refraction is close exactly 1. What does it mean? So, N is C over V, n is 1 means what? C over B is 1. So, C is equal to B. That means speed of light in vacuum is equal to the, okay, since the material is vacuum. So, speed of light in vacuum is simply 3 times 10 to the power 8 meter per second. But if you go here, so it is approximately equal to 1 because 1.0003. So, but little bit less than 3 times 10 to the power 8 meter per second, less than 3 million meter per second, right. But if you go to the water, then you will see the refractive index 1.33. So, what does it mean? If you put n is equal to 1.33, then C over B. So, velocity of the light in water, that means C over 1.33. Okay? That means if you divide the velocity of light in vacuum by 1.33, that gives the velocity of the light in water. So, it reduces significantly, right. If you go in glass, refractive index increases to 1.5. In diamond, you will have the maximum here 2.42. Significantly, speed of light is reduced when it use the medium diamond. So, one important thing in previous lecture, I told you that the electromagnetic radiation does not need actually to propagate from one medium to another medium, just like in unlike in the case of the sound waves. In sound waves, you see that you need a certain medium, predominantly you use the ear medium, right. So, you need the ear to propagate the sound wave from one place to another place, but in electromagnetic waves you do not need. Light does not need any medium as it comes from the sun to the earth, okay. But it can travel in the medium, but if it travels through the medium like glasses, water, diamond and other materials, the speed definitely gonna be slow. But one important thing you need to keep in mind, the speed of light in vacuum is always constant, which is universal constant. It never changes. So, one important thing you need to highlight here is if we increase the refractive index, okay, higher value of refractive index of the medium means the speed of light is significantly reduced with respect to the speed of light in the vacuum. Okay. So, refractive index n is equal to C over B. C the speed of light in vacuum, B the speed of light in the material. So, we know that frequency of the light does not change as it passes from one material to another material. We know that. We know the wave equation, wave speed V is equal to the lambda times f, wavelength times frequency. So, we know that the frequency remains constant, then we know that the speed of light is varying as it goes from one medium to another medium. So, if f is constant, then what else must be changed? We know the velocity is changing. So, to change the velocity, then lambda must be changed. Okay? So, that means if light goes from one medium to another medium, or electromagnetic wave travels from one medium to another medium, frequency remains same, but wavelength gonna be changed to adjust the velocity, okay, because velocity gonna be slower. So, you know the relation n is equal to C over B, you know the B is equal to lambda f. I think now you have to do these problems. This is the problem. The problem is your mobile phone transmits signals using high frequency radio waves. Assume a wavelength of 35 centimeter while traveling through air. Refractive index in air is simply the 1. What are the frequency and wavelength of the signal as it travels through a 3 millimeter thick glass window in glass, which is equal to 1.5. So, think about that. So, you have to use two formula, one is the formula of refractive index, another formula is the wave velocity. So, how we can deal this formula? Okay? First, you know the velocity is equal to the lambda f, right? Let me solve this problem. B is equal to lambda f. So, f is simply the B over lambda, okay? we need to find out the V. Okay? We need to find out the V. So, we know the N refractive indices is equal to C over V. Okay? So, in air refractive index is 1 and C is simply speed of light in vacuum and V is simply the velocity of the light in air. So, if the refractive index is 1, that means V is equal to C. Velocity of the light in vacuum is equal to the velocity of light in air. Okay? So, the frequency of that transmitted radio signal is simply, we know the V is now C since refractive index 1, then lambda, F is equal to C over lambda. So, you know the C is simply 3 times 10 to the power 8 meter per second, then lambda is simply 35 centimeter, right. 35 centimeter is equal to 0.35 meter. So, if you calculate this, you will get 8.57 times 10 to the power 8 hertz. Okay? You know the hertz. Since meter cancel, 1 over second is hertz. So, let me simplify it little bit. 8.57 times 10 to the power 8 hertz means 857 megahertz. So, we find the frequency of that radio signal is 857 megahertz. So, this remains constant throughout the propagation. Okay? So, second, we need to find out the wavelength. Okay? What are the frequency and wavelength of the signal as it travels through 3 millimeter thick glass window? Okay? So, we already found the frequency in air, then that frequency is the same no matter whatever medium you use. So, we want to find out the lambda in the glass medium. So, again you know the refractive index N is equal to C over V. So, C is C lambda V is equal to the lambda F wavelength and frequency. So, our goal is to find out the lambda wavelength, which is equal to the C n lambda. So, we know the C is simply 3 times 10 to the power 8 meter per second and the N is 1.5. Okay, N glass, N is N glass. Okay, so 1.5, no, not N lambda, it is N is equal to C over B, C over lambda F. So, lambda is simply the N F. Okay, N F. So, we know the frequency is 8.57 times 10 to the power 8 hertz. Okay. Then let me calculate this, how much I will get it. So, I found exactly 0.233 meter, which is equal to the 23.3 meter. That is how you should deal with such kind of problem. Okay, centimeter. So, this is lambda. Okay, frequency is 857 megahertz and lambda is 23.3 centimeter. Now, we are going to deal with another effect, which we call the Doppler effect. It is the big topics, but since I am going to give a little bit idea about that. So, as a fire truck passes a stationary observer, the pitch, which we call also frequency of the siren changes, right. So, in front of the truck the pitch is higher, the fire truck emits the monotonic sound. If you stay behind the truck, the pitch is lower. In other words, if a car or truck is moving while its horn is blowing, the frequency of the sound you hear is higher as the vehicle approaches you and lower as it moves away from you. This is one example of Doppler effect named for the Austrian physicist Christian Doppler, who discovered this effect. So, in general, a Doppler effect is experienced when there is a relative motion between source of waves and an observer. When the source and observer are moving toward each other, the observer hears a frequency higher than the frequency of the source. In the absence of relative motion, when the source and observer are moving away from each other, the observer hears a frequency lower than the source frequency. So, this effect is called the Doppler effect. So, the Doppler effect arises due to the relative motion between the source of the sound or source of the wave and then the observer. So, let's realize it. Okay, let's realize it. Yes, the vehicle is approaching nearby you. The pitch increases. Now it is going past to you. Now the pitch decreases. So that means the source is your vehicle, which is producing the constant frequency if we look at the reference point of that source. But you as an observer, it depends on where that vehicle is moving. Now where it is located now. Okay? That means the Doppler effect arises because of the relative motion between the observer and the source. So there may be the different situation. One, suppose this is the source of the wave, this is the observer. So there may be the different situation. Source may be the stationary, the observer may be going toward it, then observer will see the Doppler effect, change in frequency. Okay? Then the frequency emitted by the source. The observer may go away from that. In that case also Doppler effect can be observed. You can switch the situation. Now source is in motion, source is in stationary, observer is now stationary. Now source is moving. Okay? Now source is coming toward you or coming toward observer. In this case, the Doppler shift, the frequency change happen. Okay? Frequency that the source is emitting and the frequency that the observer is perceived is different, or the source may go away from the observer. There may be the another situation, both observer and the source will moving. Okay? Moving this direction, one moving this direction and one moving this direction. There are many situations. Okay? In all these situations, the bottom line is observer, either observer or the source or the both may be in the motion, should be in the motion. Then the Doppler effect is realized. Okay? This phenomenon is known as the Doppler effect. So you have the source here and you have the observer here. Let us realize it. Now source emitting the waves. Okay? Since it is stationary now, it is not, now it is start to move, then change the shift in the frequency. Okay? As listener approaches, the frequency increases, but it decreases as the listener moves away from the source. Okay? Such effect is called the Doppler effect. So one important thing, we are much more familiar with the Doppler effect in case of the sound wave, because we see the fire truck, ambulance and other things. But Doppler effect is realized, can be seen in other electromagnetic waves, like in the light, okay, in Doppler shift, okay, in astronomy that is very useful. Okay. So in electromagnetic waves also you can see the Doppler effect. So that's what I wanted to tell you. So now you have this situation, you have three observers. Level A, B and C are listening to a moving source of sound. The diagram shows the wavefront of moving source with respect to three observers. Which of the following is true? Number A, the wavefront move fastest at A, the wavefront move fastest at C, the frequency is highest at A, the frequency is highest at B, and the frequency is highest at C. You can think about that. Let us go back here. as the listener approaches, the frequency increases, but decreases as the listener moves away. Use this. So, which would be the answer? The frequency is highest at C, because C is pretty near from the source here. Okay. So, it will get the more wavefront than the point A and point B. So, it will get the more frequency. Okay. So, any relative motion between the source and the observer leads to a Doppler shift in the frequency. So, you should use this simple formula f naught, that is the observed frequency, is equal to the 1 plus v naught. V naught is simply the observer velocity if observer is in the motion, and Bs is the velocity of the source of the wave, and the v is the velocity of the wave, okay, speed of the wave, and Fs is the frequency emitted by the source of the wave. So, you can use this simple formula, not simple formula, you can use this formula to solve the problem, but one thing you have to be careful, these two can, this v naught observer velocity and the source velocity may be negative, because we are talking with the relative velocity, right. In physics 205 you learn a lot about the relative velocity. So, depending on that, where they are moving to each other with respect to each other, then v naught and Bs may be the negative. So, let us deal this problem. I think now you are in a position to solve this problem. So, the problem is this. So, a sound source is approaching you at 98 mile per hour, which means 44 meter per second. You hear the frequency as 1000 hertz. What is the true frequency of the source? So, the solution is like this. Okay. You can pause this video and you can start to solve this problem. Okay. Anyway, here is the solution. You have the velocity of the source, which is 44 meter per second, and you have frequency of the observer, which is 0 meter per second, because it is saying a sound source is approaching you. That means you are stationary. So, velocity of the observer is 0, then the velocity of the wave, you know, it is 343 meter per second, because velocity of the sound wave, okay, this is the speed of sound wave, okay, velocity of sound wave in air at 20 degree centigrade, that means room temperature, okay, 343 meter per second. Remember that the velocity of the sound wave or the speed of the sound wave is proportional to the temperature. If you increase the temperature of the air molecules, then the velocity will increase, you know, right, speed increases. So, you need to find out the true frequency of the source. Okay. You know the f naught, the frequency observed by the observer is 1000 hertz. But what would be the frequency that emitted by the source? What? So, use this formula. We know the f naught is simply the 1 plus v naught over v over 1 minus Vs over v, Fs, okay, frequency source. But we need to find out Fs, so let us rearrange it. Fs is simply the 1 minus Bs over v divided by 1 plus v naught over v, f naught. So, Fs is simply now 1 minus 44 meter per second divided by 343 meter per second. So, 1 plus 0 meter per second, 343 meter per second times 1000 hertz. So, let me calculate this. If I calculate this, I will find 872 hertz. So, what we realized doing this problem is actually the source is emitting 872 hertz frequency, but you realize that frequency 1000 hertz. So this effect, the frequency emitted by the source, real frequency, actual frequency emitted by the source, and the frequency realized by the perceived by the observer is different. This effect is called the Doppler effect. So next time I will talk about more about the light. So stay tuned, and I will try to make the more comprehensive type of videos and narrative PowerPoint that would be helpful to you to learn about this physics course. So far so good. So that's all I wanted to talk about. Please email me, or you can respond me by using the Microsoft Team, or you can contact with me by using the Microsoft Team, or you can write me in Moodle or email or any medium of virtual communications. You can use me. You can use that to reach to me. So for today, that's all. So thank you so much for your time.